or what's a continuous function and what's not. So you got to focus on the domain. Okay, is that continuity at a point thing happening at every single point that's in the domain or not? Okay, and so those are some examples of the two ways that that can go. All right. Okay, so making functions continuous. So sometimes we have a function that is discontinuous, and all it takes is one little change to make it continuous. So that's what we're going to focus on next. Okay, so got one I'd like you to take a look at here. Let's do x squared minus 9 over x minus 3. Now, on first glance, I bet most of you would tell me that this function has an infinite discontinuity, right? Come on, be honest. You look at it, it's got an x minus 3 in the denominator, and what do we always say in pre-calc? Whatever's in the denominator, that's where you find your vertical asymptotes, right? So it makes sense that you would have an infinite discontinuity here. But it's not the case, okay? Because it cancels out, all right? So factored out, this function is actually x minus 3 times x plus 3 over x minus 3. And these two factors cancel. So then we're left with f of x equals x plus 3. Okay, now, this particular function right here that we've created, I have to be able to use the original the same as this one, because they're supposed to be the same function, right? What number am I not allowed to use in this one? 3, which means because of the fact that this one came from this, I can't use a 3 in this one either. So what this looks like is kind of a little bit strange, but it looks like the line x plus 3 with a hole in it, because I can't use a 3. I can use anything but a 3, and it looks like this line. So the graph of this thing is, let's see, x plus 3. So it'd start up at 3, and it has a slope of 1, so maybe it's something kind of like that. But then when we get to 3 on the x scale, we've got to make sure we put a hole there, and then it continues on like that. So what kind of discontinuity are we looking at with this one, based on how that graph looks? I think I heard it. What kind is it? It's a removable. And another way of kind of thinking about removable, do you see how we removed a factor out of here? Okay, so that's kind of like removing that out of there. It's kind of a way to remember it. But in any event, if I wanted to make this function continuous, I would just need to plug up that hole. So right now, what we've got is f of x equals x plus 3, where x is not equal to 3. But if I allow x to equal 3, if I plug up the hole, so to speak, then I can turn this discontinuous function back into a continuous function. Okay? So one of two ways you could do that. You could write this as a piecewise function. You could say, okay, f of x equals x plus 3 when x is not equal to 3, which is what we were already at. And then when x is equal to 3, make it equal to, that would be at 6, right? So make it a 6 when x is equal to 3, and now I've basically taken a little point and just dropped it in there and filled up the hole. Or, and this doesn't always work, but in this case it does, or we could simply say, well, just drop the x not equal to 3 then, right? That would technically still work, right? So for some functions, you're going to have to do this kind of idea where you just tell them how to fill in the hole. But for this one, because we had a formula that we know that if we just ignored this fact right here, this would work. It would fill in the hole and make this discontinuous function continuous again. So we could just write out, well, just x plus 3 would do it. It would just be that line then without that hole in it anymore. Okay, so the directions for these kind of questions might seem a little bit confusing. So I'll read what they're going to say, but it's doing this kind of process. It'll say, give a formula for the extended function that is continuous at the indicated point. Basically, take the discontinuous function, this one, and make it continuous. Okay, so fill in the piece that's missing. And usually it's just going to be figuring out where's the missing point and dropping one in there and just describing what you did. Okay. All right, last thing I want to touch on, and then I'm going to be done, is the intermediate value theorem. We're not going to use this a whole ton right now, but we will in the future, so I thought it would be good to at least mention it to you guys. Okay, so say we've got some function here. And let's say this function is on some interval. It starts and it stops. Okay, it goes from A to B. And then, so this value here would be f of A. And this value here would be f of B. And what the intermediate value theorem says is, if the function is continuous from A to B, no jumps, no holes, no asymptotes, okay, every point in there, every point between A and B is a continuous point on that function, then the function should obtain every value between f of A and f of B. Outside of that, maybe, maybe not, but definitely every y value that we can pick off between these two should be represented somewhere in that function. And in this case, if we kind of shine a light on that, between f of A and f of B, right here. Because if we're starting at f of A and we end up at f of B, we're going to have to go through those points in between to get there. Does that make sense? All those y values in between f of A and f of B, if there's no breaks, if it just continually moves, you're going to have to hit every single one of those points on your way from the one to the other. Now, you might go outside of this little corridor like we did here. We dip down a little bit, but to get up to f of B, eventually you're going to have to come through there, right? You can't avoid it. And we might even go up a little bit and then come back down, but you have to go through there to get up to that point. If it's continuous, it's going to hit every single one of those in there. Okay? So that's what it says. So here's how that is, like all written out in words, like your textbook has. It says a function y equals f of x. That is continuous on an interval a to b, and it's called a closed interval because we're including a and b. Takes on every value between f of A and f of B. Okay, so in other words, another way that this gets described is if I pick some y value right here, then the x that goes with it has to be between A and B somewhere. So we'll call it f of c. Okay, so if I pick some y value, f of c, and I come over, at some point between A and B, there should be that point C. That's caught in between. Cannot avoid it. That's the intermediate value theorem. So, like we will do a little bit more with that later, but show it to you now. When we get into derivatives and that sort of thing, this is going to become really, really important. But for now, just kind of have that idea in the back of your head. So, okay, I'm going to stop there to give you guys some time to work today.